Hey everyone, Mr. Fransky here. Today we're going to be talking about logistic functions. Let's go green for Edina Hornets. So logistic functions, not to be confused with logarithmic, right? Logarithmic are logs, right? Those are the ones that look like this. Okay. All right, logistic functions. These are an interesting class of functions that actually have a lot of real-world applications. And I kind of want to talk about why, like where these come up. And you've probably seen this graph before, but I just kind of want to talk through it and see if we can figure it out. So a number of fish, enough to breed, are placed in a medium-sized lake with moderate resources. Here's our lake, and here are our fish. Yay, they're so happy. Okay. So they have no predators. That's important. If there are predators, things get confusing. If you were to graph the population size of the fish with respect to time, what do you think the graph would look like? So I think most people know that population increases exponentially, right? Population increases exponentially. If they have unlimited resources, unlimited space, just because, if every two people or two animals get together and they make, so many babies and the babies make more babies, if everyone has like 4 kids, then you're going to be multiplying by 4 for every generation. And that's exactly the definition of exponential function. But the problem here is we're restricted by a certain size, right? Medium-sized lake. Excuse me. We're not told what the size of the lake is. We don't know how much food there is, but you can assume that there's only so much food, right? So what happens is the lake has what's called a carrying capacity. So whereas an exponential model might make sense if you have unlimited resources, what happens here is the fish are going to start off by increasing really fast, and then they're going to end up leveling off. So there's some horizontal asymptote up here that's called the carrying capacity. Carrying capacity. So there's some point where usually, so right here, right, when the rate is growing the fastest, they're actually going to start leveling off because at this point you end up with too many fish in the lake, right? There isn't enough food, there isn't enough space, and eventually it levels off. So it starts off growing really fast, and they start to realize, oh my gosh, there's not enough food for everybody, and you end up hitting this level, this carrying capacity, right? And you might waver around a little bit close to it, but this is in general what a logistic function looks like. Logistic function has 2 asymptotes. This is actually one of the parent functions we already talked about way back when we did parent functions like in chapter 1. But this logistic growth model has an equation that is c over 1 plus ae to the negative kx. Now this looks kind of confusing, but it's stuff that we've been talking about, right? It's an exponential with an e. E is the e we've been talking about, 2.71828, blah, blah, blah. And let's just kind of think about what's going to go on here. So when, let's think about our intercept first. Okay, there's no x-intercepts because x-axis is a horizontal asymptote. But let's think about this point right here. So if x is 0, let's see what y is going to be. So f of 0, so if I want to find the y-intercept, I just plug in 0. So it's going to be c over 1 plus ae to the 0, because k times 0 is 0. So e to the 0 is 1, so this is going to be c over 1 plus a. So 0 comma c over 1 plus a. Oftentimes they'll ask what was the initial value or the initial population. Just plug in 0, you get c over 1 plus a, not that bad, gives you a value. You're also often asked what the carrying capacity is. Well, the carrying capacity is what we approach as x goes to infinity. So the carrying capacity is going to be the limit as x approaches positive infinity of f of x. Well, let's think about that. As x gets really, really big, let's think about what happens to e to the negative kx. E to the negative x, we know from our exponential talks, looks like this, right? So as x goes to infinity, e to the x is actually getting very, very close to 0. And the reason for that is because e to the negative kx is 1 over e to the kx. As x gets big, the bottom of this fraction gets small. As bottom of a fraction gets small, this whole thing gets very, very small. So this guy right here is turning into 0. This guy is turning into 0. 0 times a is 0. So this is going to be c over 1 plus a times 0. That's just c over 1, which is just c. So that's very easy to remember. The carrying capacity is just the number on the top. So the carrying capacity is equal to c. So whatever number's on top, that's going to be your horizontal asymptote on the top. Now the reason it approaches 0 as you go to the left is because as x goes to negative infinity, so as x goes to negative infinity, now this e to the negative kx right here, if x is going to negative infinity, the two negatives will cancel out. So you have a very big number here. A very big number times a, I don't care what a is going to make a big number. Add 1, it makes it even bigger. C is a constant, so you have a huge number on the bottom. This is getting close to 0. Because you have c over a big, big number, so that's getting very, very close to 0. So as x goes to negative infinity, the function is going to 0. As x goes to positive infinity, the function is approaching that carrying capacity, c. Now, one more thing I want to mention. If you look at the graph, and this is something that becomes very important in calculus. When is the population growing the fastest? When is it growing the fastest? Here it's growing pretty slowly. At the top, it's also growing pretty slowly. It's growing the fastest when the slope of the function is kind of the steepest, right? When it's rising the fastest. When does that happen? It happens exactly at half of the height of the carrying capacity. It's tough to prove this. You have to use calculus to prove that. But it happens at what's called the inflection point, right? So the inflection point, you may have learned about in statistics. It's kind of like when the curvature of the graph changes. But it happens halfway up. And you get a lot of questions where they'll ask, when is it growing the fastest? And you have to solve for x for when you're at half of the carrying capacity. So solving this equation, c over 1 plus a e to the negative kx, is going to happen a lot. And to solve this, we have to use logs. That's kind of why this goes hand in hand with the exponentials and logs. You can cross multiply or do the swap property, which we'll talk about when we're solving a little bit later. But it's not a real hard equation to solve, especially if you have a calculator. So let's take a look at an example. Alright, zombies are taking over Edina. Oh no! Thankfully, the police were able to put up a wall around the city quickly to contain the outbreak. Zombies convert normal people to zombies by biting them, obviously, everyone knows that. The number of zombies follows the following logistic function. So I want to talk about why it's logistic. So they put up a wall, right? So you start off with a few zombies, right? We'll find out how many in the problem. So you have our zombies, and then we have our regular humans. Right? Lots of humans. Lots and lots of humans. Okay? So what's going to happen is initially there's lots of food. Right? The zombies are eating all these people, eating their brains, biting them, whatever. And so there's lots of them to grow quickly. So initially it's growing super fast, but eventually they're starting to run out of people. There are more zombies now than humans, right? We've killed a bunch of these humans, turned them into zombies. So we have more zombies now than humans. So it's harder to find food. So it starts to level off, right? So that's why it's going to end up being logistic. Okay, so we're given this equation, and we're asking, first of all, how many zombies were there initially? Well, if you want to try these yourself, you can. They're a little tricky since we haven't done an example yet, but I'm going to go through each one kind of in detail as we go. So if you want to try it first, you can pause the video, but let's see if we can do them together. So how many zombies were there initially? That's going to happen when x equals 0. We're told here that x is measured in days. So at day 0, so x equals 0, I want to know f of 0. Or z of 0, since we're using zombies. So z of 0 is going to be 51350 divided by 1 plus 649 times e to the negative 0.2 times 0. Well, e to the 0 is 1. So this is 51350 over 1 plus 649 times 1. 649 times 1 is 649, plus 1 is 650. So we have 51350 over 650. I'm going to go to a calculator for that. I've got one ready to go here. I think it's right here. Oh, come on. There we go. All right, so we said 51350 divided by 650. Looks like 79. So that is 79. Initially, 79 zombies that are going to wreak havoc on Edina. I wonder how long it's going to take for them to turn all the people in Edina to zombies. We'll probably find out. Let's see. All right, what is the carrying capacity of the Edina zombie population? Well, remember, which is the number on the top. So it's 51350. And I actually checked, as of January 2018, that is the population of Edina, which makes sense, right? If you put up a wall around the city, there are 51,350 people, then we should only be able to convert that many to zombies. Okay? So if you were to think about the graph here, we now know that the intercept here is at 79, 079. And we know that the intercept, or the asymptote up here, sorry, it's a terrible asymptote, is at 51350. So pretty low on the totem pole down here at 79. But eventually they will get close to that carrying capacity. Maybe they don't get all the way because maybe there are some people hiding, right? I don't know. Okay. How many zombies will there be after 20 days? Well, that's just x equals 20. So we're just asking for z of 20. So z of 20 is 51350 over 1 plus 649 e to the negative 0.2 times 20. So I'm going to show you how I would do this with a calculator, because putting it all in one expression with those scientific calculators, I really only want you to use the scientific calculators for these problems, because the fancy calculators can do too much. You don't have to use change of base and stuff. So we're going to use a scientific calculator to do this. I've got plenty in the room if you want to use one. But let's take a look at how I would do this. So what I would do is I would start with this exponent right here. So I'm going to do negative 0.2. That's not negative. Oh, let's clear them all. Let's see. So we have negative 0.2. Maybe it does work. Times 20. Gives me negative 4, so I hit equals. There we go. Okay, so we get negative 4 there. Now I'm going to do e to that power. So I do e to that power. Do we have e? There it is. So I'm going to do e2. I'm going to go to second answer. So on your calculator, I think that's second 0. But I can get my previous answer by hitting the answer button right there. Okay, so now I have, hit enter on that. So now I have the 0.0183. That is e to the negative 0.2 times 20. So I'm going to multiply that by 649. So I'm going to do times 649. Let's see if they'll let me do that. Nope, I got to get my answer. So answer... Oh, let me do that. Nope, got to go back to e. All right. E to the negative 4. Enter. And then I'm going to do answer times 0.649, or 649 times 649. It's my first time using this calculator. It's a little clunky. 49, there we go. Gives me 11.886. Okay, so that's this whole part down here. Now I have to add 1. So answer plus 1. All right, and then I'm going to do 51350 divided by that. So 51350 divided by my answer. 3,984 about. So about 3,984 zombies after 20 days. Okay? No, not even to a month, and we're already almost to 4,000 zombies. They're growing quickly. Uh-oh. All right, 1 with a population of zombies equal 40,000. So now I know the population is 40,000. And I want to know what x is. 51350 divided by 1 plus 649 e to the negative 0.2x. Now, at this point, I'm going to use what I call the swap property. If you ever have like 5 equals 1 over x, the way I would solve this is multiply both sides by x. These cancel, and then divide by 5. So x equals 1 over 5. But what happened? They just switched places. You do the same thing here. You could multiply by this whole mess, right, on both sides, and then divide by 40,000. I'm just going to do what I call the swap property. It just saves a lot of headaches and easy algebra mistakes. So I'm going to do 1 plus 649 e to the negative 0.2x equal to 51350 over 40,000. Now get rid of the 1. I just subtract 1 from both sides. So that goes away. Now we divide by 649. At this point, I'm probably going to start getting into the calculator, but I divide by 649. So I have that is equal to e to the negative 0.2x. So let's figure out what that number is. So I have e to the negative 0.2x is equal to, let's go to our calculator, see if I can do better this time, 51350 over 40,000. All right, and then I'm going to take that, and what was it? Subtract 1. And then divide that by 649. Uh-oh. Go away. Oh, no. Oh, it's gone. All right. Well, I'm learning my lesson with this calculator, and I love it. 51350, let me use the calculator, or the keyboard here, divided by 649. And then minus 1, and then divided by 649. Oh, I had that wrong. Oh my goodness, I can't do anything right today. Okay, 51350. Hopefully you're skipping through this part. Divided by 40,000 minus 1. Then we take that and divide by 649. Huh, goodness. Okay. So a very small number. E negative 4 means it's 0.0004. So I have 0.004372. Now to undo an e to a power, we're going to take the natural log, right? So we're unbumping this. So we have negative 0.2x is equal to natural log of 0.000437. Last step will be divide by negative 0.2. That'll solve for x. All right, so let's take the natural log of our answer there. So natural log is right here of our answer. Okay, and then we're going to take that and divide by negative 0.2. Looks like 38.675 days. Okay, so in just over a month, we got 40,000 zombies. My goodness, that's crazy. Okay, all right, let's see what else they ask. So what will the population of zombies be when the zombie population is growing the fastest? So this is where we talked about when it's going to be the steepest slope, right? And that happens at halfway. So just half of 51350. All right, clear up. 51350 divided by 2 gives us 25675. Right? That is the y coordinate. That's the y coordinate. That's what the y value is going to be, the population of the zombies when it's growing the fastest. Now when they ask when will it occur, we have to solve it like we did last time. So that's going to be equal to 51350 over 1 plus 649 e to the negative 0.2x. Let's see if I can not mess up the calculator as much this time. So we're going to swap them. So we got, let's do it over here, 1 plus 649 e to the negative 0.2x equal to 51350 divided by 25675. All right. Subtract 1, that goes away, divide by 649. So we have e to the negative 0.2x. Let's figure out what that is. So we have 51350 divided by 25675. What should that be? It should be 2, right? 25675. There we go. Okay. And then we're going to take that and we're going to subtract 1 from it. And then I believe we're going to divide that by 649. This is going much better. Hopefully I didn't just jinx it. Okay, so 0.0015408, that's what we have right here. 0.0015408. Okay, so now we take unbump by doing natural log. So negative 0.2x is equal to natural log of 0.0015408. And then we'll divide by negative 0.2. Okay, so let's see how many days it is. Should be less than our last answer, right? Because we have fewer than 40,000. So we do natural log of our answer there. Natural log of the answer. And then we divide by negative 0.2. Oh. Answer divided by negative 0.2. 32.37 days. So just over a month is when zombies are growing the fastest. Cool. All right, that's all there is to logistic equations. Solving them is kind of the most difficult thing, being able to work with the calculator. That swap property is really handy. And then just subtract 1, divide by 649, or whatever your number is, natural log, and then divide by that negative 0.2, or whatever that k is in front. All right, I think that's all I've got for you. Yeah, looks like I have one more slide with the same questions on it. So if you want to try those again, you can. But that's it. I love you guys. That's why I'm here. Have a great day.